And right now, it is my honor to also introduce Prof. Ma'amar bin Tayyib, who is the Vice Chancellor for Research and Graduate Studies at the University of Sharjah. Thank you, Prof. Ma'amar bin Tayyib, for being with us today. The floor is yours.
Thank you, Professor Kauthar. It's really gives me my pleasure to be with you in the 7th International Conference. I have been following with Dr. Manar and her colleagues the evolution of the conference, and you really end up with a nice, rich program. I have seen the title of the presentations this afternoon, and it's really very, very interesting. A lot of papers on a broad sense of computing, from artificial intelligence to soft computing, to security, to big data or data analytics, with importantly many applications to medical, to engineering, to materials, to education, to business, to social sciences. I really liked many, many presentations, and I am looking forward to listen, hopefully, to all of them. I guess I will not conclude before reminding you that these days the feminine gender is shining. Not far from yesterday or 2 days ago, I am reading from the news, an Algerian 11-year-old Rita Grahla, an 11-year-old girl from Algeria, won the World Cup for mental accounting and mathematics with 30 countries and 1,000 contestants from the world's top deputies, including Japan, China, and United States of America. Congratulations for all these achievements, and I look forward for today's presentation. Thank you.
Thank you so much, Dr. Ma'amar. It's really a big pleasure to have you here. And now on to our keynote speaker. It is our pleasure and honor to welcome Dr. Fatma Milli, the Dean of the College of Computing and Informatics, who will be talking about from embracing AI to reshaping AI. Dr. Fatma Milli is the Dean of the College of Computing and Informatics and University of North Carolina, Charlotte, since August 2017. She came to UNC Charlotte from Purdue University, where she served as the department head of Computer Information Technology, then as Associate Dean for Educational Research and Development, and then as the founding and executive director for the TransSTEM Center. At Purdue, she led a major transformation of the undergraduate education in the College of Technology that led to its rebranding as the Purdue Polytechnic. Prior to joining Purdue, she was a faculty member as Associate Dean and a department chair in the School of Engineering and Computer Science at Auckland University in Rochester, Michigan. Thank you so much, Dr. Fatma Milli, for accepting to join us today. The floor is yours.
Thank you so much, Kauthar. Thank you, everyone. I'm thrilled to be here. I'm honored to be in such company, and I have been inspired by everything I have heard so far. Again, I'm here from UNC Charlotte, the College of Computing and Informatics, and I was very interested to hear how many parallels there are between our colleges. So life quakes, those major events that shake our beliefs and disrupt our trajectories, are frightening. We know what we are losing, but we have no idea whether we will land on our feet and where. These life quakes, as Bruce Feiler calls them, are also essential ingredients to our growth. They force us to loosen our grip on what we currently hold, surrender to some loss, and make room for a new transformed self. There is no denying that we are in the midst of a life quake. The COVID pandemic and its continuing spread and mutations, the social injustice and unrest, whether at the national or international arena, and the climate change happening before our eyes at a perceptible speed constitute such a life quake for all of us as individuals, communities, institutions, countries. And we are all scientists and researchers here. And as such, we have some unique, monumental role to play. our communities look for us for sense making, so that we put this in context, so that we can connect the dots and provide some explanations and make reasonable predictions. They look for us to equip our graduates with the human capacities the future will demand of them. They look for us to develop the science and technology that explain, predict, and cure our ills. They look for us as role models for handling major disruptions and rising to the occasion. My college, the College of Computing and Informatics at UNC Charlotte, has been striving to capture this privilege and responsibility through our discipline, computing. So, among other things, what we have done in the college, we have adopted 3 values. The first one, we acknowledge inequity and we pledge to do everything in our power to address it. Value number 2, we take responsibility for the social implications of technology. And number 3, we value community and collaboration over selfish interest and competition. I know this is very ambitious in a way, but it is work in progress. I will focus on the second value, our accountability as computer scientists and AI researchers. Progress in artificial intelligence have swiftly outpaced expectations in terms of performance and potency. There is a risk for all of us to be hypnotized by their power and surrender our moral responsibility in harnessing this power towards what matters and towards the transformation that times call for. Computing systems have done tremendous good in the world, and we all witness it every day. They have broken walls, they have crossed bridges, they have made the impossible possible and the unthinkable a reality. We cannot deny that. But we also must acknowledge that nothing is given. The good that technology does in the world is not granted. Technology is not neutral. It has the potential to do tremendous good, but it also has the potential to do evil in the world, and we witness it every day. And we need to be alert to the inequity and injustices that the systems we create perpetuate or cause. As we produce AI systems with increasing speed, capabilities, and scope, we are infiltrating every aspect of human life. We are infiltrating every decision, policy, and plan made by us, and more frequently for us and on our behalf. Designed by us, these systems have been amplifying our intentions, multiplying our mistakes, and magnifying our imperfections. Indeed, our computer systems very often reproduce, magnify, legitimize, hide disparities and inequities via the people building them and the data they are trained on and the interests they serve. So, for example, the relatively narrow profile of systems designers led to face recognition software that works very well for them, primarily white males of European descent, but very poorly for everyone else. Not to go very far, most AI systems are really built on data that is there. On most natural language processing systems derive their semantics from word associations from existing texts in which gender, race, and many other stereotypes are deeply embedded. So using these systems to create semantics for the systems that we create perpetuates gender, racial stereotypes, and many other inequities. And they do so in an opaque way and often with serious consequences. Also, we have to understand that most systems we design have stakeholders. Somebody paid for them. And it is very important for us to ask the question, who and why? Every system has stakeholders bereft of altruism. And we see examples of this in the news every day. Last year, for example, there were several articles about hospital emergency triage systems. These triage systems are sponsored not by health professionals, but by insurance companies. They calculate priority based on the estimated future of care, an estimate that is calculated from historical data. So besides the questionable ethics of such metric, what this data ended up encoding is another bias. Black patients have historically been prescribed less costly care. As a result, they were given lower priority in the triage systems, and consequently, this magnified this inequity without bringing it into light. Eventually, it did come to light, but a little bit too late for those patients that were impacted. And we continue to discover the many ways in which our computing systems, particularly machine learning systems, amplify not only our intentions, but also unintentional and subconscious biases that are deeply embedded in our way of thinking and that are not always readily accessible to us. This is the above state of affairs is not a fatality. It is a choice. Very often it's a tacit choice. And in some ways, in a very simplistic ways, using computing systems and AI to reproduce and magnify human decision-making is one aspect. And this is the one that is fraught with all of these problems. But computing systems can do much, much more to complement human thinking, to do the things that we are, for which humans are very often not sufficiently trained or don't have the capacity that computing have. And so computing systems do have huge potential to complement and develop our human capacity beyond what we have been using them for. And I'll give two examples here. Complex systems and long-term thinking. Both of them are necessary components in the formation of an equitable and sustainable world for current and future generations. The first one, complex systems. In the last century, science has been primarily reductionist, focusing on the premise that every system is the sum of its parts and that understanding the parts leads to understanding the whole. In this approach, phenomena are repeatable, explainable in terms of action and immediate reaction. And such a model is very appealing, and reductionist science has really been the source of all of the progress that we have made in the last 100 years. But as powerful as it is, this model has limited effectiveness, especially when it comes to so-called complex systems. These are systems where actions and consequences are not related on a one-to-one basis. Instead, they are not additive. It's not what I'm doing now, today, that will have this impact. It's what I am doing every day. It's what we are all doing every day that will eventually result in an impact. So it's not a single action, but the accumulation of repeated action that eventually leads to a reaction. In this system, the reaction is not immediate. So it's not if I do this now, I will see the outcome right away, but it happens with a non-negligible delay, clouding the connection. So very often we don't see that. We don't see that what we have done now resulted in this 10 years later. We don't see that this war actually resulted in these refugees 10 years later. The connections are there. They are undeniable, but we are able to ignore them because of that long delay. So in these systems, the reaction is also not deterministic at the detail level, but in the form of patterns. These actions lead to this kind of outcomes. So they cannot be understood in a reductionist fashion. And as a result, they evade our intuitive thinking and challenge our deliberate analysis. And I'm sure you agree with me, most of the challenges we face today as a society and as a human civilization are complex systems issues, whether it is climate change, race relations, socioeconomics, or geographic inequities. In all of these cases, human thinking is limited or untrained in understanding the remote but real connections between actions and inactions, and the systemic consequences we observe and experience. Computer simulation tools and age-based models have developed significantly in the last decade, enabling us to better understand, reason, and experiment with complex systems. And so in addition to the simulation tools, I see also lots of potential in education. We need to start educating our students in complex thinking and complement their intuition. But in the meantime, we have a huge potential, again, to use AI systems as a complement for current human thinking. The second area in which I think AI systems can be very powerful in complementing the limitations of human thinking, and it is of much urgent need, is long-term thinking. Humans' propensity to prioritize the urgent over the important and their gluttony for short-term gratification has been supported and encouraged by technology. And we all observe every day how technology has really trained us into that immediate gratification. And the more we do that, the harder it becomes to actually to focus on the long term. As a result, we are making decisions today that are endangering the voiceless humans of tomorrow. Our brains are unable or unwilling to grasp the connection between our actions today and the pain and suffering they generate in the future. Roman Krznaric, author of The Good Ancestor, a radical prescription for long-term thinking, describes our behavior as the present colonizing the future, whereby we treat the future as a distant colonial post where we dump ecological degradation, nuclear waste, public debt, and technological risk. At the same time, technology is a powerful resource that can be used towards more long-term thinking and higher generational equity. Scenario planning and simulations, virtual and augmented reality have proven effective tools in making the invisible visible, the abstract concrete, and the far away immediate and present. And there are not too many, but a few examples of that, where the combination of AI, virtual reality, augmented reality have been used to effectively help us see what help us connect what we do and the impact in the future. And an example in the United Arab Emirates, the lab created by Superflex allowed government officials to actually breathe the air of 2034. And they did this under different scenarios. This is, if we invest in this kind of energy, this is what the air will feel like. If we make these different decisions, this is what the air feel like. And again, we intellectually know the impact of the decisions that we are making, but breathing it is completely different. And in fact, this has led the government to make significant investment in renewable energy. So life quakes are unsettling, but they also are wake-up calls and times to reflect, re-examine, let go of the unequal, inequitable, and unsustainable world, and welcome a better version of ourselves in a more equitable world. This life quake is a wake-up call for all of us, AI researchers, AI researchers and educators affiliated with ArabWIC. This is a call for all of us to step back and be much more deliberate and intentional about our work. We are the intellectual leaders. We have the capacity and the privilege to use that intellectual capacity towards the things that are most important. Our success should not be measured in terms of incremental, one more paper, one more grant. We can measure our success in the major impact that we can make in the issues that we are facing every day. We can be more ambitious and demand that every effort, every research project be directed towards our issues, the issues that we face as a group, as a society, as a species. So ArabWIC has the talent. ArabWIC has the high level of awareness. ArabWIC researchers can together lead us towards a sustainable, just, equitable world. Thank you very much.
Thank you so much, Dr. Fatma Milad. What an inspiring speech, really intriguing. And thank you so much for sharing your vision, especially on complex systems and long-term thinking, which are much needed in today's world, and also how AI can help, accelerate or solve some of these problems. Thank you again, Dr. Fatma Milad. And right now, I think we're about to start and kick off the two parallel tracks. The first track on AI and machine learning, and the second track, which is a collection of different topics. So please, if you're joining the second track, just a reminder that we have a different Zoom link for the second track. So, we also encourage you to switch between the two tracks depending on the interest you have of the different topics. So I'd like to hand it right now to Dr. Bushra Bouqatta and also Dr. Rabab Mizuni, who are co-chairing the first track. And so Dr. Bushra, are you with us? And Dr. Rabab?
And Dr.
Yes.
Kauthar, let's remind all the participants, please rename your Zoom ID to have your full name so that it's easy for us to recognize you. Okay, and to make you co-host to share your PowerPoint for your presentation.
Yeah, thank you so much, Dr. Manar. That's an excellent point.
I will also post the second link for the track 2 in case if you have missed it. So for the track 2, please join this Zoom link, those who are in the track 2.
Thank you. Dr. Bushra and Dr. Rabab, the floor.
Thank you, Dr. Kauthar.
Good morning.
Good morning. Good afternoon.
Yes, good morning in the US and good afternoon for everyone. So welcome to the AI ML track. We're very excited to have a really good collection of excellent papers and presentations. And Arabab, if you can kick off.
Yes, sure. So thank you very much, Bushra. So we have 13 papers, all related somehow to artificial intelligence and ML. We have different domains. So the first paper is entitled Scene Generation from Backgrounds to Objects and Anything in Between, a Deep Learning Robotics Survey. So the paper, I think, will be presented by Dr. Bushra, right?
Yes, yes. Let me just, I'm just trying to figure out actually the screen sharing here. I'm so sorry for that. So that I can share my screen. I think I should be able to see it, right?
Yeah, on the bottom, there is a share screen.
It's not showing up for me. Unfortunately, I have.
Dr. Manar, can you give a Bushra?
You should have it, Dr. Bushra, because you are co-host.
Yeah,
you should be able to share. Share the screen.
Yeah, it does not. All I have is to stop and start recording, but I don't have the button for sharing the screen, unfortunately, yet.
Okay, I will make you stop, remove the co-host, and then I will make you co-host again.
Okay.
With the hope that it will work. Other than that, you might leave and come back. It should work.
Okay, let me do that. Let me do that because it's not shown up. Let me just.
We can start with the second presentation.
Sure.
So that
Yes.
we can
Yes.
save some time.
Okay. Yes, please.
Dr. Rabab.
Yes, sure. Session, a systematic literature review. So the authors are Asma, Sayam, Ali Abu Nasif, Manar, Qasim Nasir, and Bushra al-Blushi. So yes, Asma, are you going to present?
Yeah, inshallah.
Inshallah, very good. So can you please share the presentation?
Are you able to see my presentation now?
Yes.
Okay. I'm Asma Sayam, a computer engineering master student from University of Sharjah. My systematic literature review is about deep learning models to detect online false information. The agenda for my presentation, I will start with a brief introduction, objectives, related work, and then the methodology, I follow it in my systematic literature review. Finally, the results and discussions for the research question, conclusion, and the future work. The fake news term is a general concept pointing to news pollution. Fake news detection process is the task of classification and evaluation, published the news veracity, whether they are true or false news. Deep learning have the ability to identify the most effective features for learning process by itself and still performing with high accuracy and short time in comparison to machine learning and other manual ways. The objective of this systematic literature review is to help the researchers and to have a complete view of the developed deep learning models that have been proposed in the field of false information detection, the deep learning models gap in fake news detection, and how they can improve them. In addition, we are conducting answers for the following research questions. The 4 research questions, I will go through over them in details in research question and in discussion, in result discussions in the following sections. The related work, actually, there is other surveys and systematic literature reviews have been done in similar fields, but we are different than the previous, the other surveys and systematic literature review by covering fake news detection models from different aspects. We are from different aspects by including summary of developed deep learning models for false information detection that are based on textual content of the news. Also, we explore the available models and the repository of the dataset in Arabic. We are also reporting the type of content, whether they are textual or both textual and visual. Moreover, we introduce the training techniques, supervised, semi-supervised, or unsupervised, the dataset, source, language, type of input data, and what are the mostly used evaluation metrics. This systematic literature review is covering the last 5 years, starting from 2017 and beyond. The methodology of our systematic literature review. We follow Kitchenham methodology, which conducted in 3 phases: planning phase, conducting phase, and reporting the result of the review. Our systematic literature review limited to researchers that have examined deep learning models for fake news detection. They apply feature-based approach using content textual data input for Arabic and English language, including search on journal and conference paper for the last 5 years, as I mentioned before. I will go over the results and discussions. First research question in our systematic literature review is what are the deep learning algorithm, methodologies, and techniques used for detecting false information or false news. We noted that we noted from all studied research papers, journals, and articles that the most used model for deep learning for classifying fake news is CNN. As it's composing 28% of studied articles. Then we can see that 25% of research paper also use long short-term memory to overcome the problem of memory vanishing. The second question is what are different sources of fake information used to perform fake news detection and what's the dataset language? This question is divided to two parts. The first is about the dataset sources. Datasets are collected from different sources, such as fact-checking website and the news website for true news. And most researchers used for false information. They use the social media platforms, which contain huge content of fake news due to the ease of republishing online content. Our research statistics shows that 64% of selected research papers have used social media extracted dataset from Twitter especially. Unless they combine the textual content with image, then in this case they use Facebook or Instagram, but due to a Twitter policy, it's the easiest way to extract it from Twitter, as Facebook and other social networks have more policies, have more restrictions. The other part of the question is about the dataset language. We can find that only little work has been done in English, in Arabic language, where it combines only 9% of the studied articles. This is due to several challenges such as low availability of Arabic dataset, difficulty in training Arabic language dataset related to its characteristics and computational problems, and orthographic. Okay, the third question is what are the used features in classification and detection, and what's the input data type? There, to clarify, there is two approach for features. One of them is content-based feature, and the second is context-based feature. Content-based feature is language-based and visual-based techniques to extract features. Effective visual and language features can be identified, including traditional, local, and global features. And context-based can be either user-oriented or post-oriented. User-oriented distinguish account types and extracting user-specific feature, while post-oriented is seizing people's sentiments and response toward fake news. We can see that 66% of studied research and journals is using content and context, while 34% only use content. This is due to the difficulty for processing the natural language. So they need to combine it, they usually combine it with context features. The second part of the third question is regarding the input data type, whether they include text and image input or they include only text. Most of the study research paper use only text content, while 16% of research paper combine both text and image. As we know, sometimes they write the news in a picture to hide it and to overcome the fake news detection methods. The fourth question is regarding what are the used evaluation metrics and the accuracy of deep learning fake news models. The most used metrics for evaluating model performance are precision, recall, area under curve, and F1 score. It's the most used one. I find it the accuracy, and I record it in details in my research paper. The highest recorded accuracy was 99.9, but we couldn't say that this is the best model, of course, because the performance is dependent in other aspect, in many other aspects, like the data set, and the data set language, the input type, and many other aspects. The conclusion and future work can be done in this area. We can find that from our discussion and the result, that research work in fake news detection based on deep learning models on Arabic language is very limited due to several challenges. That there are no adequate dataset for Arabic language, and all available dataset are either not enough for extracting features, or they have some features that are mostly textual content. Moreover, the dataset size is small comparable to required dataset to be used for deep learning. As we know, that deep learning require a huge dataset to be able to extract the features and the processing feature. Used dataset in the literature are labeled either manually or using machine learning, what makes the sentence or the extracted dataset not much accurate, like if it is labeled by experience, or if it is labeled by experience. There is also a single proposed model, which include the OCR to extract textual content from image. We discovered that accuracy of a single model might vary depending on the dataset used to evaluate it. Therefore, there is no one-size-fits-all assessment dataset that can be used to test several models and judge the accuracy of the various methodology. The last point, that most dataset that is related to social media network is limited to Twitter and Weibo. There is very limited work has been done using Instagram or Facebook due to their policies to extract post and user information. Finally, those are the references, and there is more reference and details in my research paper. If there is any question, you are more than welcome.
Thank you very much, Asma, for the nice presentation.
Thank you all.
Any questions?
May I have a question?
Yes, sure.
Hi, thank you so much, Asma, for this excellent research paper and presentation. One question I have is, where do you see more work that needs to be done to address, the problem you're looking at, given the research literature? What are the gaps that still exist?
Actually, there is a lot of there is many gaps in this field. First one which I pointed is there is a very limited work in Arabic. So we can improve the Arabic dataset. We can improve the Arabic language processing. We also for extracting the dataset, also we need work for combining image and text together. I mentioned some of them, and more there is in my research paper, but there is a huge gap can be improved from different aspects. Even the model can be improved.
I see. And have you looked at, the latest NLP models like BERT and Roberta and, the recent ones for NLP? Are they used, to tackle these problems here? Do they perform better than traditional methods?
Up to now, no. I did not find the papers use them for natural language processing.
Okay.
Especially in fake news detection.
Okay. Thank you very much.
Thank you.
Thank you. I just have another question, Asma. So how can we identify fake news? Like based on what? Is there kind of some criteria, or did the researcher kind of find out a couple of, as I said, some criteria in order to say that these are fake news?
Can you repeat the question, Ms. Manar, Dr. Manar?
Dr. Rabab is asking you how you would define these fake news. Based on what?
Based on the
Do you have a specific criteria?
Based on natural language features.
Okay, because
By
like
extracting.
Yes, for example, we have news circulating, let's say in Twitter. So how can I identify that this is a fake news?
First, we will train the model by true news from trusted sources and fake news extracted and labeled from source. Then we can classify it depending on natural language extracted from here. There is other also approaches which use the user profile and
yes,
also use the user
type.
User replies also they sometimes, or user sentiments to identify it.
Okay. The news. Okay, thank you, Asma.
Thank you all.
So, Dr. Bushra, are you needed? Sorry, are you ready?
Yes, I have. Now I can see the
Go
screen
ahead,
sheet.
please.
Okay. All right. So. Okay, so today I will be giving a presentation concerning actually a very interesting topic which is related a little bit to the previous topic, which is generating scenes using deep learning algorithms. And the scenes could be objects, backgrounds, landscapes, interior rooms, building facades, etc. And really the motivation here is really some of the applications and why it is needed. So there are several applications now that
I'm
are...
sorry, Dr. Bushra, to interrupt you, but I cannot see your screen. So am I the only one facing this problem, or?
No, we can't see the screen.
So, Kauthar, you can see the screen?
No.
Okay.
Bushra, are you sharing?
Okay, can you see it now?
Now we can see the screen, but
now it works. Okay, can you see the presentation? Okay.
Yes, perfect.
Okay.
Thank you.
Okay. So as I was saying, there's actually a lot of applications right now that really it makes use of deep learning algorithms. For example, like self-driving cars, fashion try-on, design of interior rooms and buildings, and also architecture for architecture design in gaming, and different other applications like other robotic applications, for example. But the challenge with a lot of these deep learning algorithms is that they are very data hungry. And unfortunately, in order to collect data that is enough for training these algorithms, that means you have to deploy them in the field. And in some cases, it's just not possible, or it is just too dangerous. For example, like for self-driving cars, you cannot just deploy them to collect the data at that scale. Or, for example, in designing like games, for example, you just simply don't have such data to collect. So one way that actually now the trend has been is really to move towards synthetic data generation. And in this case, not synthetic data generation that is done manually, but actually using machine learning and deep learning to generate this synthetic data. So this is kind of like one of the aspects of machine learning for machine learning. And one way that these models actually are used, there's a set of models called generative models. So we're used with the supervised learning models, where you have an input, you do know the inputs and the outputs label, and then you train the model according to examples and samples that you have. And then it learns basically what's the pattern in your data. The other extreme, which is the unsupervised learning models, these are the models where you don't really have that input-output pairs. and you still try to understand what's going on and really generate something in this case. And then there is also like a difference between generating some model, generating content, or for example, when you have a model, you generate an example, and in some cases you give it an input, or the input is just a random number. And this is one of the very popular generative models that actually are used for generating a lot of synthetic data that is used, especially in computer vision and images, for self-driving cars, for example, or fashion try-ons, or robotics per se, is GANs, so generative adversarial networks. I'm not going to go into a deep detail in this. There is a lot of, I have references in the paper, really good references for if people want to dive into it. But there is a very interesting concept, and the reason why I'm showing this is that you provide Z, which is it's a value, it's a random noise that either has a Gaussian or uniform distribution. And that actually, what it does, it just gives a representation, can be thought of as a latent representation of the image in the latent space. And that actually what generates, what helps this type of models to generate different samples every time. And it's not exactly the same image, but it's slightly different. And in generative adversarial networks, also what they have discriminator, where you can still say, okay, so I wanted to generate something, but I want it to be closer in this domain. For example, I want it to be landscapes, and I don't want it to be, for example, oranges or bananas or other objects. And then that basically helps it really reiterate and converge to some nicely generated images. Now, since GANs have been introduced, there have been a lot, like long way through, it seems long, but it's actually just a few years, and actually now it's evolving very fast. A lot of algorithms have been based on GANs. So one that's very famous, and probably people have seen it, it's called cycle GANs, which is is translating an image into an image. For example, you have a photo, a regular photo into a Monet painting, or you have here horses into zebras and zebras into horses, or you can change actually like a season. You have a scenery and you change a season from one season to another, like summer to winter and so on and so forth. So this is cool, which is nice. So you can do this translation, but actually some of these cases, like changing summer to winter or day to night, actually it's very useful when dealing with self-driving cars, for example, because you might have the scene for the day, but then you want to have a scene of how it will look like at night, and this type of algorithms will be very helpful for that. So here are some examples, and as an evolution on top of kind of like cycle GANs, there is an algorithm called pix-to-pix, and this algorithm, actually, I'm sorry, I just lost my there. Pix-to-pix is actually one of the very first algorithms, and a lot of algorithms are built on top of that really started looking at, you provided with an input. It's called a segmentation map. Like here is a segmentation. So for example, the way it is taken is that you might have a ground truth image, and then it extracts a segmentation map that identifies each color code here, actually, or label, identify different things. For example, green ones are for buildings, and then these blue ones here are for cars, etc. And then what it does, it generates an output that is similar, but it's not exactly one-to-one to that. And then I talked about this day to night and night to day. Then another one is with building facades as well. However, if you look at this is there are a lot of artifacts here. You can see a lot of artifacts in this early generation of these type of models. And then there is another type of model which actually allows you or allows the user to actually define what they want to see in the scene. And here, and this is called the DC GAN, and it is actually a type of GAN that learns the manifold of the natural image, for example, the natural image, and then it allows for manipulations in the latent space to come up with something that is similar, and uses actually this is very early rudimentary way of a lot of defining what, for example, here you want to see something like a mountain. It can interpret it as a mountain, or it could be interpreted as a house, or it could be like, for example, here you can interpret it as a church, depending on what is the target image or what is the target landscape you're giving it, and it tries to extract something that is similar to it. However, we still see that there are a lot of artifacts in this early stages of this type of algorithms. One that actually became very, very famous, it's called SPADE, and famously called Gauguin, based on the famous artist Gauguin. And this one, actually, what it does, you give it here. This is a nice segmentation map. You start, and the labels. Most of these actually are labels for landscapes, labels like a tree, sky, grass, etc., and sea. And then you give it a target image or a target landscape, and it tries to come up with an interpretation of these labels in the latent space that reflects this target image. And here you can see here, for example, you can see the sunset, while in here the sun is not present in the target image, so you don't see it. And in some cases, it really creates some really nice, super realistic, not realistic, but really rather not realistic, but supernatural effects. However, one of the challenges with this type of algorithm is that you still have, you can only, there are some labels here that are actually stronger than others. And then in order for you to be very precise and have actually a really nice, clean, these are cherry picked basically. So these are nice, outputs here, but sometimes you have some outputs that really don't, you have some distortions and defects in the images. So with that, there has been actually some other involvement in the in this space, and it's another algorithm called Sean, so which is built on top of SPADE, and makes some modifications where actually it does actually address the interpretation. So the way they do it is that they add one more layer where they feed also feeds the semantic layout as input to the deep network, and then process it through the stacks of convolution and normalization. So it adds it again so that it makes it kind of like reemphasizes it and makes it more neater and also more precise. So for example, here, like if we look at sometimes of some of the buildings, they're better. Like here, the road, it is more defined and less. You have less artifacts. Okay, so as a conclusion, so using GANs for synthetic data generation, it's very powerful, especially in applications where large amounts of data is needed, but it's not available. It's kind of like the horse before, or the carriage before the horse, rather, because you need to have the data to train the model, but you need to have the model very well so that you can deploy it and then gather more data. So synthetic data really helps in that aspect and shortens the time for deploying some of these applications. However, these type of algorithms, they fall short in controlling the generation of the data that is needed, because again, you have because of this latent space interpretation that is sometimes hard to manipulate. And you have to be very, very careful. And some of the algorithms, they now allow you to provide some input as well for the latent space so that you can control it a little bit and control specific things. However, when we are talking about complex scenes, like for example, a scene in an urban setting where you have buildings and you have several things, one way is to look at it is to think about procedural synthetic data generation, where you actually learn from real data or manually prepared synthetic data and then generate new samples. So this is kind of like every time you reinforce the algorithm so that it generates something that is a little bit more realistic. Now, if you want something that is fantastic, then coming up with latent space parameters that lets you explore different ways and coming up with different things is it's still acceptable. And with that, I will stop and see if you have any questions for me.
Thank you, Bushra.
Yeah, thank you so much, Bushra. I have a small question. Just wanted to check if you have looked at basically the performance of the deep neural networks that use synthetic data compared to real data. Like, do you have like any idea how well the synthetic data generation works? Does it, give the same performance in terms of neural network accuracy, or there is some degradation?
So yes, so actually that's a very good question, Dr. Kautar. Actually in some applications like in robotics and self-driving cars, I've came across and I've also experienced it myself, where we have synthetic data that we are using for training these algorithms. When we just leave the synthetic data as it is and we feed it to the for training, for example, we do see the performance is not optimal. So what we do, and this is why I call the procedural kind of like interpretation or procedural fact, which is you introduce a human in the loop a little bit, or kind of like manual, like for example, some data labeling, some data manipulation that is done manually, and you feed it again to these algorithms so that these synthetic data becomes looks more real. And a good example would be, for example, the light of the day and night, or the light inside of a lab setting might be okay from a perspective in general if you look at it, but then if you have some specific lighting conditions, let's say cameras and things like that, and you want to really replicate those lighting conditions because that's what your algorithm is going to be seeing in the field, then you need to do some manipulations there to get it closer to what is your real environment is. Otherwise, in general, I mean, it does help with the augmenting your data, but definitely a lot of manipulation is needed on top of that.
So Dr. Bushra, do you see mostly the manipulation happening in the like the data processing phase, or can we also solve this by doing some hyperparameter tuning and optimization while training the network?
So one of the interesting techniques also. So there are it's several folds, right? So one is the pre-processing, the sometimes data labeling, and helping the algorithm kind of like think of it as not completely unsupervised. It's kind of like a reinforcement learning type of thing, where you have you provide some kind of feedback to the algorithm in terms of what was generated and whether it is closer to what you want or not, right? So that they have these discriminators where you can inject some either some real data from the field so that it gets closer to what you want, or and the hyperparameter fine-tuning, it can help, but not so much. The problem here is that because it's highly unsupervised. These are unsupervised algorithms. The only way, excuse me, really is to see how you can give them some feedback without really manipulating them too much. Some algorithms, actually, in some techniques, people have been trying to manipulate the latent space. The latent space, this is really where all the generation and the projections of what the images that will be generated happens, and that manipulating the latent space is a little bit tricky, and it's really the interpretation of what value in a latent space means from a human perspective. So there are some algorithms now that they have some interfaces that allow you to dial in some numbers that makes a little bit more sense to humans. And this one actually, I did not tackle it in this paper, but it's actually like in face generation or facial manipulation. Like you want someone older, but how much old you want the hair to look different, but how much you want some very minor features that you want to change, and that's basically you're manipulating the latent space. But really translating the latent space into parameters that are human readable and interpretable, that's one of the challenges.
Thank you very much, Dr. Boshra. Very interesting. Okay, so let's move on with the third paper. Cloud-based network intrusion detection system using deep learning. Arshana, the authors are Arshana. Sorry. Keitra, I hope that I'm pronouncing right your names. I'm sorry for that. So Kuchi, Pratishka, and Sivarman.
Okay.
Yes.